Alright, this is going to be a video concerning some of the examples from chapter 14, so you'll be able to see how to work problems. First one is 14.3. It says, suppose waves travel with a speed of 2 meters per second and a wavelength of 1.5. Then these waves are going to go into a shallower region, but the frequency is going to be the same. So we are going to use the equation velocity. Frequency times wavelength. I'm going to plug in my velocity and I'm going to solve for the frequency. So if I'm a frequency, 2 divided by 1.5, that's going to give us 1.3 hertz. Now the frequency is going to remain the same, so when I go to the shallow region, I'm going to use the same equation. It says my speed decreases to 1.6. The frequency is 1.3, and I'm going to find my wavelength. So I'm going to take 1.6 divided by 1.3. And that's going to get me 1.2 meters. And that has two significant figures. Okay, the next one is number 29. It says sound has a frequency of 425 hertz, and what's the wavelength? We're going to be using the same equation, but now we're going to need to know the speed of sound in air, and that is 343 meters per second. It's in your book, but anything that has sound with it, you're going to have that number as long as it's moving through air. So my frequency is 425, and they want me to find the wavelength. So 343 divided by 425. And my wavelength is going to be 0.807. That has three significant figures. And part B wants to know if the frequency is increased, what happens to the wavelength? Well, if velocity is staying the same, that means these two are inversely proportional. So it means they do the opposite. So if one gets bigger, the other gets smaller, and vice versa. So in this case, if the frequency is increased, then the wavelength has to decrease. And the velocity is always the same in the same medium, just the frequency and the wavelength will be changing. Alright, the next one, you hear a rock drop into a well, and you hear the splash 1.5 seconds later, and they want to know how deep the well is. So I'm going to use distance is rate times time. My rate is still the speed of sound, 343, and my time is 1.5. And so my distance is going to be 514.5, and I only get two significant figures, so that's going to be 500. I'm going to have to write it like that so that it has two significant figures. Now, if this were an echo like it is in your assignment, in that case, an echo would start here. It would have to go down to the bottom of the well, and then it would be traveling back up. So if the time that they give you is, let's say, 1.5 seconds for you to hear the echo, then that means it's only half of that time to get down to the bottom. But in this case, they weren't asking for an echo. Okay, the next one says we have violins, and they're talking about decibels. So in this case, we have an equation that relates decibels to intensity. Okay, I is your intensity. I0 is the intensity, the threshold of hearing, which is 1 times 10 to the minus 12 watts per meter squared. Alright, so I'm going to plug in my decibel reading, 82.5. And I'm going to solve for my intensity. So the first thing I'm going to do is divide by 10. And then the to do is do the inverse log. And the inverse log is 10 to the x. So I'm going to do 10 to the 8.25, and then I'm going to be multiplying by 1 times 10 to the negative 12th. And I got 1.78 times 10 to the minus 4th is my intensity. Now that's for 20 violins, so I'm going to have to divide by 20 to get me the intensity of 1, which is going to be 8.89 times 10 to the minus 6th watts per meter squared. Alright, then part B says if the number of violins was increased to 40, will the intensity be more, less than, or equal to 165? So I'm going to have to find the decibels if I have 40 violins. Alright, so 8.89 times 10 to the negative 6. I'm going to take that times 40, and I got 3.556 times 10 to the negative 4th. Divided by 1 to the negative 12th. And then I'm going to do the log of that answer, and then take it times 10. And I got 85.5. So for 20 violins, it was 82.5. For 40, it's 85.5, and that is much less than the 165. So that's what they want to know for part B. Alright, the next one is using the Doppler effect. And we're going to need to find the right equation. And for an object that is moving, we have 1 plus or minus mu over v times f. If the source is moving, this goes on the bottom. If the observer is moving, this part goes on the top, and then it's over 1. And if both are moving, then you have this 1 plus or minus mu over v on the top and the bottom. And in this case, toward is a negative, and away from you is a positive. So this frequency is the new frequency that we hear, and we detect a frequency of 470. And mu is going to be how fast the object is traveling, and v is the speed of sound in air, which is 343. And then f is going to be my original frequency, which is 450. Alright, so first I'm going to take 470 divided by 450. 1.044. 1 over 1 minus mu over 343. Okay, so then I'm going to take 1.044 times that, or 1. So I'm going to take 1 divided by that number. So 1 divided by that is that number, and that's going to equal 1. My eraser here. So 1 minus mu over 343 equal to 0.95744. So then U over 343 is going to be this number minus 1. And I have two negatives, so those will go away. And then I multiply that by 343. 14.5957, and it looks like I need two significant figures. So 15. Meters per second is how fast the car is moving. Alright, in this one we're going to take a look at harmonics, and it says that this is 14.75, and there's a drawing in the book, so I'm going to draw a drawing on here. One end is going to be closed, so this is the closed end, and the other end is open. Alright, so if I have a closed pipe on one end and open on the other, then I know that I only have odd harmonics, and I know that my wavelength is going to be 4L divided by the harmonic. If this was a string, or if both ends were open, then I'm going to use 2L divided by the harmonic, and I can get all of them. So in this case, only odds. First thing I have to do is figure out what harmonic this would be. So the first place that I could have it be open would be right here at this first antinode. That is going to be my first harmonic. So the next harmonic that I would have possible would be right here. So this is going to be the third harmonic. So I could find my wavelength of the third harmonic. I'm going to take 4 times the length, which is 2.75. And I'm going to divide by, oh, this is supposed to be my harmonic, divide by my third harmonic. Alright, and that is going to tell me what my wavelength is. My wavelength is 3.67. Now in this case, they wanted me to find my fundamental frequency. So velocity is frequency times the wavelength. So my velocity is 343. Frequency, and my wavelength is 3.67. So this is the wavelength of the third harmonic. So I'm going to put 3 here. So 343 divided by that is going to give me a frequency of the third harmonic, which is 93.545 Hertz. Now the fundamental frequency is going to be the lowest frequency, which is the first harmonic. And in order for me to find the first harmonic, I'm going to have to take this by 3, because the frequency of the third harmonic would be 3 times the fundamental frequency. So 93.545 is equal to 3 times f. So if I divide by 3, then the frequency of my fundamental is 31.1818. And it looks like I'm going to get 3 significant figures. So 31.2 Hertz. It's going to be the frequency of my fundamental. So this is, there's about 3 things I need to know, or 4. First, since I have one end open, I only get odd harmonics. That's the equation that we're going to use to find the wavelength. Like I said, it's 2L divided by the harmonic if we are dealing both ends closed or both ends open, or if it's a string. This one we've used before. And then the last one is going to be that the frequency of whatever my harmonic is, frequency of that harmonic, is the harmonic times the fundamental frequency. So I kind of used 4 equations for that one. Okay, and last one says that I have a tuner, hits a key on a piano of 261 Hertz, and here's 3 beats. What are the possible frequencies? Well, the difference in the beat frequencies, or the difference in the 2 frequencies, is my beat frequency. So since my beat frequency is 3, then that means it's either 3 higher than that or 3 lower than that. So if I add 3, so I'm going to take 261 plus or minus 3. So I'm going to have 264 hertz is 1. And then if I take 261 minus 3, that's going to get me my other one, which is 258 hertz. So those are the two possible frequencies that it could be. And that concludes the examples from chapter 14.